So metal testing lab, experiment number 10, tensile test. Aim to conduct the tensile test on mild steel and to study the following: verification of muscular behavior of mild steel under the action of gradually increasing load. Third, to determine the yield stress, tensile strength, Young's modulus, percent elongation, percent reduction in area. Apparatus: universal testing machine, specimen, vernier caliper. Procedure: operate the upper beam and handle and hold the specimen tightly. Keep the both right and left side valves fully closed condition. Start the hydraulic motor. Open the right side valve slowly such that the upper beam is slowly moving upwards. Separate the geared motor and adjust the up-down position of middle beam to suit the clamping of test piece. Operate the jaw handle with the middle beam to clamp lower position of the specimen. Lock the jaws in the position by operating the jaws by lock handle. Turn the right control valve slowly to open the position till you get the desired load reading rate. Stop turning the valve once the rate is set. Note down the readings. Observations. Note down the original diameter of the specimen DO. So original diameter of the specimen DO. Note down write down the original gauge length LO. So measure the original gauge length LO of the specimen, that is 90 mm. So diameter of the fracture, this is after the conduction of experiment. Gauge length after fracture, this is after the conduction of experiment. Original cross section area, that is AO is pi by 4 DO square. So DO square, the original diameter, the square. Using this formula, calculate the area of cross section. Cross section of the area after fracture, this is after the completion of experiment. Draw the tabular column with load, elongation delta L, stress and strain. So take the readings which we get from the experiment. Hold the specimen into the jaws of upper and lower jaws of the UTM machine and lock it in the position. Switch on the on position and rotate the right hand wheel to open position. The screen will show the load versus the elongation for that load. So note down at particular moments, note down the load and corresponding elongation. Now gradually increase the load and note down the corresponding load and elongation in the load and elongation columns. So go on taking the readings. At equal at every interval of load and elongation. The specimen is being pulled apart with a tensile load. So keep taking the readings at regular intervals and note it down for load versus elongation. Note it down corresponding load and elongation. Reading taken from the display. So after 79 kilonewtons, after reaching to a point of 79 kilonewtons, the load is gradually decreasing. It means that it has crossed the ultimate point. So now the curve is going down. So now after some time, fracture may take place. So it has already reached the ultimate point. It has crossed the ultimate point. Now it is going towards the fracture point. As you can see, a neck formation below the specimen. Neck formation is trying to happen. So this happens when it has crossed the ultimate point, and after some time a fracture will take place at this point. Vale, straight there.
67. 66 are there. Very good. 65.
ಇಷ್ಟು ಪುರಾವೆ ಆತದೆ 3 2. Straight. So the reading shows the peak load at 79.35 and peak elongation as 11.78. So these are the readings which we get from the display, and the braking load was near 58 kilonewtons, which we found on the display. The specimen is removed from the jaws. So these are the broken specimen. So it forms a necking. So it forms a necking at the breaking point in the form of cup and cone. So this we call it as the cup, and here we call it as the cone. So it's called cup and cone fracture of tensile. Now joining this two, once again take the so now take the reading of the final gauge length. So this is the neck diameter. So calculate the neck diameter or diameter of the fracture, 9.5. Now calculate the final length or final gauge length, that is 105. So after test, note down the final length of the specimen and final diameter of the specimen and final cross section area of the specimen, that is pi by 4, neck diameter the whole square. So we get the final cross section of the specimen. Also calculate so the stress and strain using these two values of load and elongation for each points. So for each point calculate the stress and strain for all the readings. Now calculation. So first one, yield stress of the specimen. Yield stress is yield load upon original area of cross section. So yield load can be recognized with the sound while conducting the experiment. So the yield was near 54 kilonewtons. So divided by original area, we get the yield stress. The ultimate stress of the specimens. Ultimate stress is the peak load or maximum load upon original area. So your peak load was 79 or 80 10⁻³ upon original area. So you get the ultimate stress or maximum stress of the specimen. Now breaking stress. So breaking stress is breaking load upon original area. So breaking load, so we got it at near 58 kilonewton 10⁻³ upon original area. We get the breaking stress. Dividing these two, we get breaking stress. Now percentage elongation is final length minus original upon original length into 100. So final length minus original length upon original length into 100. We get percentage elongation. Next, fifth one, percentage reduction in area. So original length minus final length upon original length into 100. We get the percentage reduction in area. Lastly, Young's modulus of the given specimen. So from the graph, we need to find this Young's modulus. A graph is plotted on load versus elongation. So each point of the readings is plotted on this graph. So as you can see, it's a perfect stress strain curve of a mild steel. So by taking the slope of this graph, slope of this initial graph, you get the Young's modulus, that is stress by strain. To divide the stress by strain, by taking the slope, we get the Young's modulus in GPa.